lesson, we are going to discuss proofs. And in particular, we're going to examine proofs in the context of geometry. Ultimately, we're going to spend today seeing how to write up a two-column proof. Now, we've already done this with algebra. Now we're going to start seeing it with geometry. One of the ultimate goals in a geometry class is to prove theorems using our deductive reasoning. Using and analyzing logic will help us formulate the plan for a proof, and then we have to carry it out with the details. Only two pieces of quick vocabulary. We have a theorem, and we have a two-column proof. One of the characteristics behind any proof, which we've discussed already, a proof is an explanation. It's a series of things that we know are true and the reasons why we know they are true. When you write up your proof, you can use words, you can use symbols, you can use basically whatever you want. But the important characteristic behind it is it needs to be clear. If I'm reading what you're writing down and I don't understand what you're trying to tell me, we've got a problem because you're not communicating effectively. In general, a proof is going to follow a structure where we will start off with our hypothesis. Usually these are the things that we are given to be true. Once you've got the hypothesis to begin the problem, you're going to start applying all kinds of things that you already know. We know that definitions are true. We know that postulates and theorems and properties. We have a list of things that are true. These will be our justifications. These are the reasons why we know things work. We'll start with our hypothesis, usually what's given, build on it with things that we know are true as justifications, and ultimately lead ourselves toward a conclusion. The conclusion is going to be the goal behind the problem. What is it that we are trying to prove? We saw with our previous work that we can have a given statement and a proved statement, and we can sometimes need to fill in the blanks in the middle. All right, the first type of prop we wish to work with is this. Over on the left-hand side with steps 1, 2, 3, 4, we have the things that are true with a proof. Our goal here is to explain why. Every one of these statements on the left-hand column are true. In the right-hand column, we need to explain why we know they're true. What is it? Where did it come from? How does it, basically, how do we know? Starting off, write a justification for each step, given that B is the midpoint of AC, and AB is congruent to EF. So step number 1, B is the midpoint of AC. How do we know that's true? Because they told us to. They told us that right at the beginning. We were given that it was true. Okay, step 2 then. Segment AB is congruent to segment BC. Why? Why do we know that those two pieces are the same? One of the things you want to keep in mind, of course, is that each line we would like if it were to tie into the one from before. Line 1 should lead us to line 2. When we read the first step, B is the midpoint, midpoint should tell us something. That's a mathematical term. We can use definitions about midpoints. We can use theorems about midpoints. We can use these things. So which one is it? Are we going to use a midpoint theorem, or are we using the definition of a midpoint? Going back to our earlier unit, we should remember that this piece right here is the definition of what midpoint is. A midpoint of a segment cuts it into left and right hand sides that are congruent. That's exactly what happened for step number 2. We know that AB has to be congruent to BC because the definition of midpoint tells us that's what will happen. Now we'll progress to step number 3. AB is congruent to EF. Why do we know that segment AB is congruent to segment EF? Going right back to what because we were told it was. We were given that they are congruent. So now we know AB is the same as BC. We know AB is the same as EF. Together, that tells us BC is congruent to EF. What will allow us to say BAB is congruent? AB is the same as BC. AB is the same as EF. What allows us to bridge that gap? This goes back to our warm-up. That's an example of the transitive property. AB is the same as BC. AB is the same as EF. So if these two things are the same, so would the next pair have to be? That's where we were going. And here's our proof then. We have our 2-column proof. The list of things that we know are true on the left, and the list of reasons why we know they're true on the right. One of the main things that we'd like to work with are called theorems. And theorems are nothing more than statements that you can prove. One of the advantages of that is after you have proven a theorem, it is now something that you know is true. As something that you know is true, you can use it as a justification for all future proofs. Basically, they will serve as shortcuts so that instead of having 12 lines in a proof, you can cut it down to 6 lines. Or maybe instead of having 6 lines, you can cut it down to 3. Theorems will be shortcuts that will make things simpler for you. For instance, our first theorem that we're going to prove is called the linear pair theorem. And I'll blow this up for you just so that you can see it a little bit better. But what we'd like to observe with that symbolic notation, if you have 2 angles that form a linear pair, then that will force the 2 angles to be supplementary. You'll notice the hypothesis and conclusion written out here with our blue. 2 angles form a linear pair. Well, this is saying 2 angles A and B, but the letters are not important. It can be angle X and angle 1, angle BAC and angle MLN. As long as you have 2 angles that form a linear pair, they will then be supplementary. Why? This is a statement. I'm claiming this is true. We want to know why. Now, just to help us understand this a little bit further, a picture can really help you understand some problems. This is one that says, if you have a linear pair, so if you wind up having a picture that looks like this, and this doesn't have to be the entire picture, it can be a piece of a bigger picture. If you see behavior like this, then it will allow you to create an equation saying that the angles will add up to 180, because that's what supplementary is. Here's the power of the linear pair theorem. It will allow us to translate from a beginning picture into an algebraic equation. And we've already seen frequently throughout the class that geometry a lot of times is about recognizing something, and then based on the thing that you recognize, you'll use knowledge that you're supposed to have to create something in algebra. Geometry will frequently create an algebra problem, and because you've got skills with algebra, you can then use your skills to get the answer. So we have a second theorem as well. This one is called the congruent supplements theorem. This one says if two angles are supplementary to the same angle, or possibly the two congruent angles, then the two angles are congruent. The symbolic logic here is a little bit more complex. We have an angle that is supplementary, and just to try to clear it up, if we have angle 1 supplementary to angle 2 and angle 3. So one angle is supplementary to two angles. Then angle 1 is congruent to angle 3. Sometimes I've had students write up an abbreviation. I hope that you remember that I said earlier with this lesson, as long as you can effectively communicate what you're trying to say, you can write down whatever symbols you'd like. The piece in the black is how I think. I know that most students aren't going to have my level of comfort with symbolic logic, so I've had students put down things like an angle is supplementary to two angles. Says those two angles are congruent. I don't know if that part in the blue makes more sense. I've seen students write things out like that. You're still effectively communicating the same idea, so I've got no problem if you want to do that. And of course, if you remember the name of the theorem, you can always just reference it by name, the congruent supplements theorem. That's fine. This particular one works like this. Let's say angle 1 is supplementary, and I'm going to say angle 2 is an 80-degree angle, just so that I think by using numbers it'll be easier to understand. So that's our angle 2. Angle 1 is also supplementary to angle 3. Where this type of thing will get used is if angle 1 is supplementary to 80 degrees, what do you instantly know about angle 1? Well, if they're supplementary, they add up to 180. So angle 1 plus 80 will equal 180. That tells us angle 1 has to be 100 degrees. And if angle 1 is supplementary to angle 3, that's still going to be 180 degrees. So basically, what this is telling us then is if angle 1 is 100 and 100, what winds up happening then is these two pieces would wind up being the same. Basically, this theorem is building around the idea that we don't need to know the actual numbers. If we know angle 1 is supplementary with angle 2, and we know that angle 1 is supplementary with angle 3, it doesn't matter how big angle 1 is. We don't need to know the number for it. It's enough to know that these two pieces will have to be the same because of a relationship like the one we were just looking at. Now, furthermore, we've already seen a couple of two-column proofs. Just want to remind you again, in a two-column proof, the left-hand column are things that we know are true. The right-hand column are the reasons why we know they are true. They are typically going to start with a given statement, and they will end with your proved statement. Beginning and end are the hypothesis and conclusion for your goal. Thus, complete this two-column proof. Basically, let's fill in the blanks. we are given a segment xy, and we want to prove xy is congruent to xy. You'll remember that this piece is called the reflexive property. Essentially, we are proving that the reflexive property is true, so that in the future, when we want to use it, we don't have to do 3 lines. We can simply say, because of the reflexive property, and do it in 1 line. So, what is it that we were given? Okay. We were given the segment xy. Why is it then that the distance xy will equal the distance xy? And this is where we get some kind of tricky thought. That's the reflexive property. But here's the piece that you've got to be careful about. We're looking at it and saying, wait a minute, why is it that we can use the reflexive property to prove the reflexive property? We can't use a theorem to prove that the theorem is true. It's like saying, well, why is the sky blue? Well, the sky is blue because the sky is blue. That's meaningless. That doesn't work for geometry. By the way, if you care, the sky is blue because our Earth scatters light at different wavelengths, and our atmosphere scatters the light that comes into Earth, and the most frequent wavelength of light that gets scattered is blue. At least the light that the human eye can actually visually see. There are other light colors that we can't see. For instance, we can't see infrared light, and it's still here. So anyhow, coming back to the problem, why is it that we can use the reflexive property? Because we are actually using the reflexive property of equality. We know that the reflexive property is true for numbers. We are using the fact that it's true for numbers to then show that it's also true for segments. We're building that additional layer of complexity. We'd expect that it should be. This is our reason why. Lastly, we have the definition of congruent segments. That's our prove step. Segment xy is congruent to segment xy. You'll notice the problem begins with the given and it ends with the prove. That's how a 2-column proof, that's how all proofs should be. Then we've just got to figure out the reasons in the middle. Okay, here's a little bit of a longer one. This is the proof of the congruent supplements theorem, the one that we were just looking at. So we have the given statements, angle 1 and angle 2 are supplementary. And angle 2 and angle 3 are supplementary, so we need to prove angle 1 is congruent to angle 3. Once we prove this theorem, we will then be able to use it forever. Anytime we want to use it, we will be allowed to because we now know that it's true. So, over here with statement A, what is it that we know is true? What is it that we were given? Because our reason is that we were given that it's true, so what were we given? Angle 1 is supplementary to angle 2, and angle 2 is supplementary to angle 3. Clean up this a little bit. There, we have our statement. From there, see how it builds. We have supplementary. Then, what does supplementary mean? We know supplementary means that the two angles will add up to equal 180 degrees. So now that we know they're supplementary, we can see then we will apply the definition of supplementary angles to get these two equations. The measure of angle 1 plus the measure of angle 2 equals 180. The measure of angle 2 plus the measure of angle 3 equals 180. Now that we have those two things, we have these pieces. Next we will apply substitution, and it will give us here. Well, if we're going to use substitution, that means we're plugging one thing in for another. We're plugging something in when it's the same. What do we have that's the same? Look at the problem and see. Going back up, do you see something that is the same as each other? How about here? 180 is the same as 180, so we can substitute those in for each other. Our substitution step then is going to combine those two equations. In particular, we would have the measure of angle 1 plus the measure of angle 2 will equal 180, but we already know that the measure of angle 2 plus the measure of angle 3 is 180. So we can combine the two equations into this one equation. Make an observation here that when we have the reflexive property of equality, that tells us the measure of angle 2 is equal to the measure of angle 2. Obviously, this piece is the same as that piece. We're just making a quick observation. What would you want to do to this equation then? Because we're looking down into the proof and seeing, after applying the reflexive property, we wind up getting the measure of angle 1 equals the measure of angle 3. What did we do to this equation B to get it down to here? If we subtract off measure of angle 2 from both sides, we see that those cancel. That's how we would create measure of angle 1 equals the measure of angle 3. That's how we created this part. What lets us do that? One of our algebraic properties. What lets us subtract the number from both sides? And that was, as McKenna told me, the subtraction property of equality. We're allowed to subtract the same number from both sides, and it doesn't change anything. Having done that, we now know that the measure of angle 1 equals the measure of angle 3. When we apply the definition of congruent segments, what would we get to finish? What should every proof end with? A proof should end with your proved statement, so the last line should absolutely be that. Moreover, we should recognize that the definition of congruent segments tells us that if they're the same size, that they are congruent. The definition of congruent angles tells us if they're the same size, they are congruent. Well, this line number 5 right here says we know that angles are the same size. Line 6 says, so they are congruent. And we've filled in everything that we needed to. All the pieces that we had in blue, those are the steps that we needed to have written down to fill in the blanks. One of the greatest difficulties behind writing a proof isn't so much the fill in the blank style, it's when you have to design one yourself. When you have to do the whole thing start to finish from scratch, a lot of times students will look at it and say, I don't know what to do, I don't know where to start. One of the best places is, first of all, start with a picture. If you don't have a picture that's true, draw one. If they don't give you one, draw one. Once you've got the picture, you want to start mapping out your logic, saying, I know the hypothesis, I know the conclusion, and try to fill in some of the big steps, some of the major things that you're going to need. And if you can identify the big steps, then a lot of times the small details fall into line as you're writing it. So, 2 more theorems to work with here. The right angle congruence theorem is one that should be really, really kind of obvious. All right angles are congruent. We'll use the abbreviation right angles are congruent. Essentially, this one is saying, over here, I have angle A, that's a right angle. Over here, I have angle B, that is a right angle. Those are congruent to each other. Why would they be congruent to each other? What's the big picture idea? If it's a right angle, it's a 90-degree angle. So if they're both 90-degree angles, that makes them congruent, because angles of the same measure are congruent. It's the definition. The congruent complements theorem is virtually identical to the congruent supplements theorem. Just switch out the word supplementary with complementary. So this would be used to say if angle 1 is complementary with angle 2, and then angle 2 is complementary to angle 3, those two things combined tell us angle 1 is congruent to angle 3. The rationale behind it is here. Suppose we knew that angle 2 was 40 degrees. Well, if that's 40 degrees, what does it force angle 1 to be? Since they're complementary, they have to add up to 90. That would force angle 1 to be 50. On the second line, 40 plus something equals 90. Once again, that would force it to be 50, and since 50 matches 50, the angles are congruent. That's the idea behind the proof. Alright, so here's what we would have to work with. This is the congruent supplements theorem. Angle 1 and angle 2 are supplementary. Well, similar to it. Here's our given. Angle 1 and angle 2 are supplementary. Angle 1 is congruent to angle 3. So we want to prove angle 3 and angle 2 are supplementary. Our plan, if we're consistently using the word supplementary and we've got congruent, it makes sense that we should know what the definitions of those things are. We can use the definition of supplementary. We can use the definition of congruent. Our plan is to use those definitions and start making a substitution. If we are going to show that they are supplementary, that means we need to show that they add to 180 degrees. Well, that's going to be our goal. The end result is if we show that the measure of angle 3 plus the measure of angle 2 equals 180, the definition will tell us, I know that these are supplementary. That's how we'll begin. So, from start to finish, what do we have? We know that we should always start with the given. What is it that we were given as true? We were given angle 1 and angle 2 are supplementary. were also given angle 1 is congruent to angle 3. So what do those things mean? We can use the definition of supplementary and create something. What does that mean? Supplementary angles tell us that they have to add up to 180. We were also given that they are congruent. Angle 1 and angle 3 are congruent. We can use the definition of congruent angles. What does the definition of congruent angles tell us? It tells us those have to be equal. So now what? At this stage, you would need to recognize something. Measure of angle 1, measure of angle 1. We can apply substitution here. And we can plug it in. Measure of angle 3 replaces the measure of angle 1, that's what we had in the blue, into that equation. And this is a piece where, just as an additional piece that may be helpful, I'm going to put down lines 2 and 3 here, just as an additional comment to say, look, this is where I'm working. It's not something that's necessary, but it just helps communicate a little bit better. Then what? Well, this is exactly what we were trying to get. According to the definition of supplementary angles, angle 3 is supplementary to angle 2. And we're done. Please notice the structure for how these things come together. It's important that you recognize that the problem is always going to start out with the given. Inside the given, you will have terms. You will have supplementary, you have congruent. Recognizing the terms in the given, that's what tells you where you should proceed. It tells you what you need to do next. Having supplementary led us directly to using the definition. Having congruent led directly to using congruence. When we're told that we have something, we're going to use those. Once we put those pieces together, then we can start seeing how things start fitting. We would need to make the observation here about substitution. But once you make that substitution step, once you recognize it, everything falls into place and our proof is finished. But all of that hinged on the fact that you know how to start with the given, and it hinged on the fact that you were looking at what you were actually given. Those words tell you where to go next. That's all that we had then. We're trying to build familiarity with the two-column proof. In particular, our primary goal, ultimately, we want you to be able to write a proof up like this on your own. Filling in the blank is kind of nice. Providing the justifications like we did in example 1 are nice. But those are providing you with just an additional structure, trying to help you learn. The ultimate goal is this, that you can read a statement and figure out how to create your own proof and then write up the details. It's a very high-level skill. It's not something that we expect you to get just, overnight. We'll continue to work on it throughout the year. We'll continue to work on proofs in several different contexts, on lines, in triangles, in quadrilaterals, with circles. We'll do proofs with 3D shapes. We'll use proof throughout the year again and again and again. This is just step one or step two of many, many, many steps. Building your skills so that you can eventually prove things on your own with comfort.